Hello again, OChem students. Once again, we are working with molecular models this week, and in particular, we're going to be focusing on cyclohexane. For example, if you put 3 carbons in a ring, you have a highly unstable molecule, a cyclopropane, and cyclopropane by default must have a 60-degree angle inside the ring, which is very distorted from the ideal 109-degree angle. This creates what we call angle strain. And also, if you rotate it up, you can see that right around each of the sets of CC bonds, we have torsional strain due to eclipsing interactions. If you move to 4 carbons, you would find that, again, if you made it all planar, you'd have 90-degree internal angle, somewhat strained from 109, and again, you'd have all eclipsing interactions at every bond that lines up. However, the more stable conformation of cyclobutane actually bends a little bit, contracting the internal angle slightly, but allowing the bonds to remain somewhat staggered, so they're not completely eclipsed. As we go to 5 carbons, a pentagon actually has exactly a 109-degree internal angle, which is great if it's all planar. But again, when you make an all-planar cyclic compound, you have a whole bunch of torsional strain from eclipsing interactions. So the actual 5-membered ring forms what we usually call the envelope conformation, where it distorts out of a plane in order to remove a lot of that torsional strain. You can look down these bonds now and see that they're no longer fully eclipsed. And by doing that, it actually compresses the angles a little bit below 109. Okay, if we go to cyclohexane, if cyclohexane were forced to be flat, we would have 120-degree internal angles. That's what a hexagon requires. So we would have significant angle strain, and like these smaller rings, if we force cyclohexane to be flat, we'd also get eclipsing interactions at each of the carbon-hydrogen bonds. So in fact, cyclohexane prefers to do another conformation in which it rotates somewhat around its bonds to form a so-called chair. In this chair, every single carbon-carbon bond and carbon-hydrogen bond is able to maintain exactly a 109-degree angle, and looking down any 2 of those bonds, you'll see a perfectly staggered conformation. So the chair conformation is by far the most stable of the conformations that cyclohexane can form. There is another major conformation with about 109-degree angles called a boat that creates some eclipsing interactions and some steric interactions. However, the chair is the most important, and there are in fact 2 chairs that any one cyclohexane can form. One end is down or the other end is down, and these are the low energy conformations at both ends. There's a chair, and it goes through a series of rotations to get to the other chair at the other end. The OChem Magic Virtual Molecular Model Kit also has a cyclohexane C6H12 that can be loaded, and you can rotate around and look at from multiple angles. Again, you can see the chair-like conformation, and I want you to notice specifically there are some hydrogens in the chair that go up, some that go down, and some that are around the middle. These hydrogens have unique roles in the cyclohexane chair. Okay, the best way to deal with cyclohexane or any conformational issue is with plastic models, and once again I've made up a plastic model of both cyclohexane with the ball and stick models and the straight bond models. I actually prefer the straight bond models for doing conformational analysis, but either one of them works. So let's start with the ball and stick models. Okay, with the ball and stick models, if you first build your model, you're going to end up with something that looks sort of weirdly shaped. You can actually force it to be flat with these 120-degree internal angles, except it's kind of unhappy that way. You can look down bonds and see conformational torsion. But the actual chair can be made by grabbing every other atom and making it go upwards, and every other atom and making it go downwards. So if I count around the ring, 1, 2, 3, 4, 5, 6, carbons 1, 3, and 5 will have one of their groups facing straight up, and 2, 4, and 6 will have one of their groups facing straight down. Then you know you've got a chair. And this actually illustrates, and I've done it with colors here, 2 unique kinds of hydrogens that are on every single carbon in a chair. In particular, one of the hydrogens on each carbon is facing straight up or straight down. I've got them all indicated here with white atoms. These are the so-called axial hydrogens. They're like the axes of the globe. They point to the north and to the south. Every carbon also has a second attachment, which is facing more or less around the outside, the belt. This is called the equatorial hydrogens, not unlike the equator on a globe. So you've got your axials up and down, pointing to the north and south pole, and you've got your equatorials right around the equator of the chair. Once you make a chair, you can look down any of the two bonds, and if you have a proper chair, they should all be staggered. Okay, so there's the head of the chair, there's the foot of the chair, so it's kind of like a lounge chair for a Barbie doll. Okay, so you've got your chair, and you could change this chair so that the head becomes the foot of the lounge chair. Think of those chairs that you use outside, and the foot becomes the head. And what you'll discover is you once again have 3 straight up, 3 groups straight down in the alternative chair. However, every group that was equatorial, pointing around the middle, is now pointing up and down, the reds. Everything that was axial, the whites, are now equatorial. So you know you've changed from one chair to the other if all the axials have become equatorial and vice versa. So I'm going to redo this. And again, with this model set, you got to help it a bit to get into that chair by squeezing together the 1, 3, 5, 2, 4, 6 to make the ups and downs. Alternatively, if you're using the stick models, it's actually a little easier to do, because when you put together the stick models, they're going to naturally want to maintain 109-degree angles that are enabled by the chair conformation. Once again, I've indicated all the axials very clearly by putting red balls on them in this case, and the equatorials I've left with empty sticks. And if I change to the alternative chair, which happens very readily with this model set, you can see that all the reds now become equatorial and the blacks axial. Okay, now we're going to talk a little bit about how to draw a chair. A chair is drawn as a perspective drawing in which it is tipped so that we can see sort of edge on and all of the groups attached. And it's drawn by doing the following steps. First, we draw 3 pairs of parallel lines. These represent the frontmost and backmost carbon-carbon bonds in the cyclohexane. Then we draw 2 parallel lines pointing down and up from either end. Finally, we draw 2 additional parallel lines to join the 6 carbons together. So now we have 1, 2, 3, 4, 5, 6 carbons in a ring looking end on, and here's the head of our chair. At the head of the chair, or anything that's pointing up in our drawing, we put a flagpole going straight up. Flagpole here on the sides of the chairs, and at the foot of the chair, or anything that has a point going down, we put a well straight down. These are our axial groups on each of these carbon atoms. For example, this carbon atom right here has an axial down. We can also draw in the equatorial groups, and they're going to be approximately in between each of the axials and approximately the middle or equator of the ring. And again, we're looking edge on to a 1, 2, 3, 4, 5, 6 carbon ring, each of which has an axial either going up or down, up or down, up or down, and it also has an equatorial, approximately in the equatorial direction. This is how you draw a cyclohexane.